Welcome to Open Collaboration Hydrology, the podcast that is all about using cutting-edge technology and collaborative approaches to drive innovation in water science. I'm Ines, your host, and I'm excited to guide you through the world of open collaboration. Our approach involves a diverse network of collaborators just like you, who use everything from hydrological models to social media to make a positive impact in water management. In this podcast, we will explore the benefits of open collaboration in hydrology, share inspiring stories of successful collaborations, and discuss the challenges yet to be overcome. So, whether you are a seasoned hydrologist, a curious listener, or somebody who cares about water, we invite you to join us. Let's get it started.
Computational hydrological models are computer representations of water systems. They serve as decision-making tools for water managers and research tools for hydrologists to test theories. So, how are models built? When I came across computational models, I just fell in love. The opportunity to simulate the possible outcome for decisions about water and get to know possible scenarios was attractive to me. Hydrological models are usually built by hydrologists working in university laboratories or consultants who have been challenged to solve a water management problem or an unsolved hydrological theory mystery. There are two ways to build these models: the conventional and the participatory way. Let's talk about the conventional way. This conventional way to build hydrological models covers several stages that I will summarize as follows. In the first stage, hydrologists, researchers, or consultants define the problem. Questions as what is the water science questions that the model means to help to answer? Why a computational hydrological tool is needed to solve this question? And what are the resources available, like time, money, human resources, or information? In this first stage, the hydrologists engage with the problem by identifying the study area, reading farmer studies, and checking the most available data. By the end of this stage, the modeler usually runs away and never comes back. Joking. Well, the fact is, by the end of this stage, the modeler realizes the problem's complexity. In the second stage, the hydrologist usually proceeds to collect data. This means using different sources, such as online databases, governmental databases, or satellite information, to collect information about the topography, climate data, land use, and stream flow data of the basin. In some cases, a new installation of instrumentation is needed. In particular, when the model is built to expand the hydrological theories. Researchers usually set up field instrumentation in a control base to make experiments that will be tested using the hydrological model. The overall objective of this stage is to collect as much data accessible as possible. By the end of this stage, the modeler should have a repository with the information available. However, collecting data also means reviewing it, correcting its errors, and transforming its formats to a format comparable with the tools that the hydrologist uses. For instance, instead of using Excel files, the hydrologist might want to use text files, or vice versa. This stage is rarely done in a solo journey. the modeler usually belongs to a team where some coworkers are exclusively dedicated to this stage of development. Parallel to the former two stages, the hydrologist may choose to visit the field site. The goal of the field visit is to get a better knowledge of the water system processes and check the reliability of the data. For instance, to see at first sight if the land cover information is trustworthy, or to check if there is something in the runoff processes that must be considered. In so many cases, the hydrologist doesn't live in the basin. This means they need a first-hand perception of the field, so the field visit is essential. In instances where the model is built to test hydrological theories, field visits are usually used to get insights into the water system processes and nourish the hydrological approaches to be tested with the model. In the third stage, the hydrologist builds what is known as the perceptual model. By using the available water system science knowledge and using their own perceptions, the hydrologist makes a mental model of the water system. In this stage, it is crucial to have a clear understanding of the behavior of the water cycle in the basin. It is also essential to review the initial problem identification questions, because the goal is to identify and capture the most critical processes of the water cycle in the basin that have an impact on the main problem under study. The result of this stage is usually a handmade scheme full of arrows representing the water fluxes in the basin. In the first stage, the hydrologist chooses a model structure. This means the modeler chooses the appropriate type of model to simulate hydrological processes in the catchment. In hydrology, there are several types of models that we will discuss further in this podcast. What is important here is that the hydrologist determines the type of mathematical expressions, parameters, and constants that will be used to simulate the water system. More importantly, the hydrologist decides whether to build the model from scratch or use a pre-existing model to simulate the water system. This decision sometimes is decisive in the success of the project. Building a model from scratch might be time and money consuming, whereas the decision to use a pre-existing model might influence the quality of the project. Several hydrologists suggest that the modelers must make this decision wisely. A typical error is trying to use the models that you know most for every single project. Like, when you know you have a good hammer, everything looks like a nail. Another bias could be attempting to build a new model when there are several well-established and stable versions of models available that approach the same problem that you try to approach. So, most importantly, by making this decision, the modeler decides on any simplifications necessary to make the model comprehensive. And somehow, the modeler privileges some processes over others. For instance, the model can attempt to reproduce the amount of surface water better, rather than its spatial distribution. In this case, the model might be better for water availability studies rather than flood studies. In the fifth stage, the modeler gets the procedural model, which depends on whether the model is built from scratch or if it is a pre-existing model. Suppose the model is a novel model. Then the modeler will attempt to use a computer-based language to automate the mathematical expression that describes the theories that the modeler built in the former stages. In other words, use a computer to solve the mathematical expressions that were proposed before. On the other hand, if the model is a pre-existing model, the modeler must run it, which can sometimes be more complex than building a model from scratch. I totally understand that some technical terms can be confusing, especially if you are new to this. When we say run the model, we are referring to the process of installing and compiling a model on your computer. But run the model also means preparing the data for feeding the model. In this stage, modelers use several computational tools like computer languages to transform data so that the model can read it and use it. If a model user guide is available, refer to it when you feel stuck. It will be a lifesaver. Once the model is operational, it runs on a computer and delivers outcomes. All the effort until now paid off, and the modeler is ready to play with the model. This means checking how much the model outcomes approximate to the observed data and building scenarios to get answers to the initial questions. This is a part of the process that will be discussed in our next episode.
Thanks for tuning in to Open Collaboration Hydrology, the podcast. We hope you enjoyed this episode. Share your thoughts with us and spread the knowledge with your friends. Follow us on social media for more exciting content. Until next time, keep open collaboration in hydrology.